which, it uses cryptographic groups, actually specifically pairing friendly groups. It is transparent. It's sort of, most people think of, when they talk about pairing-based cryptography coming up in snark design, they're typically thinking of KZG commitments, which need a trusted setup, or growth 16, which is closely related to KZG commitments and needs a trusted setup. Dory is a little bit funny, or it's actually transparent, but uses pairings, sort of unique there. So typically, if you encounter pairings in snark design, they go hand in hand with the trusted setup, but Dory is an exception. Okay, and so, two nice properties of Dory are logarithmic verifier time and proof size. So this is an improvement. You can think of it an improvement over bulletproofs, which has logarithmic proof size, but very slow verifier time. On the other hand, the Dory proofs, while asymptotically the same as bulletproofs, are concretely an order of magnitude bigger. So that was a good thing about Dory, asymptotically anyway. Nice short proofs, nice fast verifier. As I said, it's transparent if you care about that. And its commitment key size is square root. So if you want to commit to a polynomial of size n, the commitment key size for Dory is square root n, while bulletproofs would be linear in n. Okay, so
quick question about that. When you say square root and like the size, what is the size that you're referring to at the polynomial? Is that degree?
Yeah, so in the univariate case, that's just degree. In the multilinear case, it is how do I want to say this? Like the number of coefficients. So more precisely, if it's like a L variate multilinear polynomial, the size is actually 2 to the L. Okay, because one way to think of it is an interpolating set for multilinear polynomials and L variables is like 0, 1 to the L, and that has size 2 to the L. So it's 2 to the L degrees of freedom. Yeah. So let's just call it the number of coefficients is what n is here. Okay, so square root n commitment key size, and it's like just random group elements. That's basically what transparent means in this context. And I think this sort of thing is about to matter a bunch. I was hoping to release a paper that cares a lot about this already. It looks like I'll release it either later today or tomorrow. So maybe next week we'll discuss this more. So these are all good things. I flagged that logarithmic verifier time and proof size is sort of an asymptotic statement, and concretely the proofs are kind of big relative to bulletproofs. But the other stuff is both concretely and asymptotically all very good. So the big sort of negative about Dory is that it uses elliptic curves at all. So let's say the big X here is uses elliptic curves. That means one, it's not post-quantum. Okay, because quantum computers can compute discrete logarithms efficiently, which renders the Dory commitments, as with bulletproofs and KZG, not binding, and so the snarks just aren't sound if you use those in the presence of quantum cheating provers. And also, this forces you to work over, certain kinds of fields, so 256-bit fields, and up. Whereas, there's no, how do I want to say this? At least if you're using the sum check protocol as your polynomial IOP, there would be no other, restriction on what field you work over, other than that the field be big enough to ensure soundness, like 128-bit field or up or something. So this whole need to work over 256-bit fields, that's coming from the use of elliptic curves and nowhere else in the snark, at least for some snarks. Okay, so today we're going to talk about other commitment schemes that don't have this downside. So we're going to start talking about hashing-based commitment schemes.
Excuse me, is it a good moment to ask a question about Dory, which was last
Yeah,
time?
well, it's as good as any. Hopefully, the answer is quick, or I'll punt. So go ahead.
Yeah, in the book, there was okay. Let me start from a little bit another end. Um I was asking last session if if the commitment key, if commitment key uh, is universal or per instance, and you answered that it is universal, and then in the book I saw that you introduced there a gamma, a big gamma, which denotes uh, part of this key. And my question is, without without preprocessing, would this gamma be an ephemeral key?
Oh, I don't think it's ephemeral, but you do. I mean, Dory, you need linear time pre-processing in Dory if you want a fast verifier. There's no way around that. But yeah, that gamma. The way I sort of conceptualize it is like Dory is a lot like bulletproofs, which has a linear size commitment key. But in Dory, you also in pre-processing have a key that lets you commit to each half of the bulletproofs commitment key. So not only do you have like a size n key, but you have a size n/2 key that can be used to commit to the left half of the size n key and the right half of the size n key. And I think that's what that gamma is, if I remember right. Although it's been a while since I looked at the book's treatment of
Yeah,
Dory.
it's not very much like it.
Yeah, so that's what so that gamma is just like another part of the commitment key that is really used to commit to two halves of like the bulletproof commitment key sort of. And then separately you're going to want another commitment key of size n/4 that kind of lets you commit to the two halves of gamma, and then another key of size n/8 that lets you commit to the two halves of that. And in fact, you don't need a fresh commitment key like every time. So it's like well, things get a little complicated because you kind of have a key for group G1 and a key for G2 and so forth. But the gist is like everything you see there in the book's treatment, these keys, they're all sort of permanent. Like the Dory committer needs to know those keys forever. The Dory verifier is ultimately only going to need to know logarithmically many group elements, which what are those logarithmically many group elements? It's just like the commitment to the left half and the right half of the bulletproof key, and then the commitments to the left and right half of that, and the commitments to the left and right half of of that key, and all the way down. So the prover kind of needs to know everything, all of these like size n/2, size n/4 keys. But the verifier does not. The verifier only needs to know like two log n group elements or something. Does that clear things up at all?
Uh, the question arises mostly because uh, while reading, it seemed that this gamma part of the commitment, I don't know how to call it better, uh, is based just on randomness that brought either by prover, either it can be brought by the one who mm, who is doing the processing.
Oh, I see. No, I think you should think of it as just another commitment key, the same way that bulletproofs has a linear size commitment key of random group elements. So like in the end, I think Dory is like, you have these two groups, G1 and G2, and you kind of imagine you're going to run like bulletproofs like in both groups, right? So there's like a linear size commitment key, which is just random group elements in G1. I'll call it G, and then a linear size commitment key in G2, call it G prime. And then you're gonna want a key in each group of half the size, which the book calls gamma, and I'm pretty sure it can just be like the first half of G and the first half of G prime. But let me just call it gamma and gamma prime, which is so this is size n, this is size n, these are size n over 2. And again, I think that literally it can be overlapping with the first I don't think it has to be fresh random group elements. But anyway, so this is size n over 2. And then then we have something of size n over 4 in each group. Okay, and if you sum up all these sizes, it's like if bulletproofs had a key size for bulletproof of just G, which is size n, I think Dory, like summing up all the G1 elements would be size 2n in G1, but then you also do it in G2. So that would be size 4n, but then like I said, gamma, I don't believe it actually has to be like independent independent of G. I think gamma can just be the left half of G. Gamma prime prime can be the left half of gamma, all the way down. And so in the end, I'm pretty sure like the Dory key size, commitment key size, winds up being like n G1 elements and NG2 elements. So let's just say the total key size, commitment key size in Dory is n G1 elements and NG2 elements. Which is in bulletproofs it'd just be NG1 elements. You don't even need pairings. So G1 is kind of a misnomer there. So G2 elements tend to be 2 times as big as G1 elements. So the total size here would be equivalent to like 3n G1 elements in size. But then when we actually apply Dory, you get like this n turns out to be like actually square roots of the real n. Anyway, so is that a little bit helpful in how to think about all these group elements floating around in Dory? And again, they're all just totally random group elements. The fact that they're totally random is what ensures that like no one knows the discrete log of one with respect to another. Yeah.
Yeah, helps about thinking. Still, I guess I will need a little bit more thinking about if it is really a published ephemeral key, if this uh, quite exotic thing is true for it, or I'm just confusing things.
Okay. Yeah. Sounds
And
good. Yeah.
another thing that you just mentioned was that this gamma isn't needed to verify. Am I got you correct just now?
Yeah, that's right. That's right. What the verifier ultimately needs is just like a commitment to the left and right half of G under gamma, and then a commitment to the left and right half of gamma under gamma prime prime, and so on, like all the way down. And so in the end, that's like 2 log n G1 elements and 2 log n G2 elements or something like that. So while gamma gamma has size n over 2, it's really big. The verifier doesn't need to know gamma, basically because in pre-processing it winds up getting handed a commitment to the left and right halves of gamma under gamma prime prime as the key, and that's enough for the verifier.
So Verify needs just a kind of small part of gamma.
Exactly. So this pre-processing phase, the way I think about it
Mhm.
is it kind of takes these big like linear size objects, of random group elements, and it compresses them down into sort of commitments to their left and right halves, and like that's all. The verifier only needs the commitments to the big objects and not the big objects themselves.
I may be wrong, but that sounds a little bit like GKR. GKR.
Yeah, everything is related in a sense. I mean, Dory can this bulletproofs is some check. And Dory is like a variation of bulletproof, so it also is some check. And then GKR, of course, is just repeated application of some check. So they're all sort of doing the same thing in ways that can even be made formal. So they should be reminiscent of each other. Yeah.
Thank you. That's a lot. Thank you.
Yeah. Thanks for the questions. Okay, so coming back to hashing-based commitments. So there are no elliptic curves in these commitment schemes, and so they are plausibly post-quantum secure. People think that they're faster, and one big reason people think that they're faster is you do not have to work over 256-bit fields when you use these hashing-based commitments. I think that that's somewhere between incorrect and right, but in a highly nuanced way. This view that like hashing based commitments are fast and curve based commitments are slow. And today, the nuances will start, I think, to become a little clearer, because this is the first time we'll be talking about these hashing based commitment schemes. So those are the two reasons people like hashing-based commitment schemes. I'd say one is post-quantum security. The other is, they have a reputation for high performance, and I think that reputation, kind of needs to be updated. All right, so let's dive in. So what are popular hashing-based commitment schemes? So examples of them. So the most popular one is FRI. The reason this is most popular, I would say, is because amongst the hashing-based commitment schemes, it has the shortest proofs. And generally, I am, sharing all of my opinions today. My view is that the snarks that have become popular tend to be optimized for verifier costs, like short proofs, and not for prover costs. So, so FRI has the shortest proofs in this class of hashing-based snarks, but it sort of is just a fact that it's significantly slower than the other commitment schemes in this class that I will list shortly.
We're here. Slower means proving time.
Yes, slower for proving time. Of course, it's faster for verifier time, just because that tends to correlate with proof size, bulletproofs being the main exception. So by slower, I mean proving time, yeah. FRI has a reputation for a fast prover, but I think that is in comparison to curve-based snarks, not to the other hashing-based commitment schemes. And furthermore, as I have repeated twice already, I think that reputation is largely misplaced. So short proofs for FRI, but slower prover than the ones I'm about to cover. Now, how short are the proofs? They're actually not that short. So think roughly like 100 kilobytes and up. I'll also mention there are new kind of advancements over FRI, like stir, and what's the latest? Sorry, I'm blanking on the name of the latest improvement to stir. That have even shorter proofs, but concretely they're in the same ballpark. It's not a huge improvement. So let's just say stir and other very recent improvements, get a little shorter than 100 kilobytes, depending on security level and things like that. These are still pretty big proofs, 100 kilobytes and or so, right? Like KZG, commitments can lead to like 1 kilobyte proofs. for things like KZG, so you're talking multiple orders of magnitude, bigger than some of the, curve-based commitments. The hashing-based stuff just leads to bigger proofs than the curve-based stuff. Okay, so that's FRI. The stuff with bigger proofs but a faster prover, that's all hashing-based. These include Ligero, Brakedown, let's see, Binius, Blaze is a new one, etc. And these tend to have, the fastest prover, biggest proof situation is like root n size proofs here. Now the term like Binius has sort of, gotten overloaded a little bit already, even though it's only a year old, where the first Binius commitment scheme was like a refinement to Breakdown and had square root n size proofs. But now there's kind of an analog of FRI called FRI Binius, which, is sort of a variation of FRI. And so this would have the same, even it's a very similar name, but ultimately it has the same properties as FRI itself of like, polylogarithmic rather than square root n size proofs. Okay, so yeah, so hiding some nuances. Like a year ago anyway, it would have been fair to just say, hey, you have FRI with its polylog proof size, concretely 100 kilobytes and up, and then you have like Ligero and Breakdown with their square root proof size, but an order of magnitude faster prover than FRI. And since then, there's been so much work that has sort of, made the picture a little less clean as progress, has filled in more points on the trade-off curve and things like that. Okay, and so today what I want to cover is like Ligero, Breakdown, and Binius, basically. And Blaze as well, falls into the same framework. And then in some future session, we'll cover FRI in full detail. Let me pause here. Does anyone want to ask any questions?
There is a question about what performances does stir and whir make over FRI? Is it proving time or anything else?
Yeah, great. So stir anyway, I have cached. So concretely, it's not a major proof size improvement. I think, in some parameter regimes, it's up to a 2x, but those parameter regimes are not actually like what people use in deployments. So I think, in deployments, it's maybe 30% or, so some marginal concrete improvement, but asymptotically, it's actually a major improvement. Okay. So FRI proof size is, and so the improvement is in proof size and not in prover time. If anything, stir is a marginally slower prover than FRI. So the FRI proof size, what is it? It's order lambda times log squared n hashes. Okay. And so, by the way, a little, kind of a pet peeve of mine. People often omit the lambda. They say it's order log squared n. Lambda actually needs to be super logarithmic. So if you're going to omit the lambda, you really should write like more than log cubed n. So just dropping the lambda is like not that's not an accurate thing. So so this is actually more than this, more than log cubed n hashes. So I don't know if you want to conceptualize this, like think of lambda as like 128, and log squared n, I tend to think of n as often like 20, so log squared of that is like 400. Okay, and there's some constant factors that can help here, but you're generally dealing with like stick 2 zeros there, 40,000 hashes. Up to some constant factors. And that's where 100 kilobytes comes from. If you work it out, 40,000 hashes is a lot of hashes. It leads to 100 kilobyte proofs, and up can even lead to like 500 kilobyte proofs. If you want 128 bits of security without any conjectures, stuff like that. So stir, asymptotically, it's really a major improvement. So this log squared n goes down to, I think, log n log n. So it almost just gets rid of one of the log factors. So that's really nice. But concretely, it just like doesn't really work out to be a major improvement. I'm pretty sure I might, I don't think it improves the proof size further. I think what it does is it speeds up the verifier, I think. So let's leave it at that. I don't want to say something totally wrong, so I won't try to go any further than that. I possibly already said something a little bit wrong there. Anyway, so high level, stir and whir are making the proofs of FRI even shorter. They are not helping the prover, and I guess it's a little bit TBD still in practice how good they are. I think I saw that the stir folks actually implemented the stir verifier in Solidity, and it's like 2 million gas or something in some parameters. I think this was like 80 bits of security, which I consider too low. But also, I think it was unamortized. So when people use FRI, they often commit to like dozens or hundreds of polynomials, and they kind of only have to produce like one evaluation proof for all, dozens or hundreds of committed polynomials. And I think this 2 million gas was just for one polynomial. And I don't think stir amortizes quite as well as FRI. So anyway, so everything here is focused on better verifier costs, and it's definite progress, but I think still the verifier costs are decently high. Okay, other questions?
In that wrap up, you just said verifier costs, and I just want to check that you meant verifier costs, not prover costs.
Yeah.
Okay.
Yeah. So like FRI, stir, whir, like they all have the best verifiers amongst these hashing based snarks, but there's still pretty high verifier costs relative to the curve based things. And that is why what almost all projects do today, if they want to, but because hashing based things have a reputation for speed, everybody wants to use the hashing based commitment schemes like FRI, for a fast prover. But if you actually run the verifier on chain for the hashing based thing, you get like many millions of gas. So no one wants to do that. So the Starkware does that, but no one else does that. So everyone else, what they'll do is they will use a curve based snark like Plonk or Grow16 to prove they know the hashing based proof. And they do that to get, so they kind of get the fast prover of the hashing based thing, which again, I think is, not actually that fast, but, I'll keep, advocating that view as we go. And, but then they get the better verifier costs of the curve based thing, at the last second before the proof goes on chain.
But then they also have to do another proof, right? Because aren't Growth 16 proofs like very intensive to generate?
Yeah, so there's been, tons of work. I mean, this was one of the major themes in like snark deployments. I mean, this was the whole point of like Plonky 2, when it came out. There's been all this work to make it not quite so painful to, like use something, to do this, to prove, another proof. Right. So like Plonky 2 does a lot of as much recursion as it can with the hashing based stuff before finally going to, actually, I think Polygon switched over to FFlonk a couple years ago, but they used to use they either use Grow16 or Plonk before that. Anyway, FFlonk is meant to like really, really, really minimize on-chain, verifier costs. So it's like an even slower prover than Plonk, but better verifier costs.
I think I'm feeling kind of just confused about this idea that like we're picking our first layer of commitment scheme to reduce prover cost, or to, like we're trying to bring prover time down, but then we add in this other layer where prover time is very large. So haven't we just like canceled out the benefit that we got?
Yeah, perfect. So the key point is that the recursive proving is proving a proof. So that is proving you apply the slow prover proof system to the snark verifier. So as long as the first snark with the fast prover has decently somewhat cheap verification, and really just like asymptotically speaking, like only sublinear verifier time is enough, right? Like so that's what ensures that the snark verifier, is just cheaper than the original statements, being proven. So what's going on is like you apply the slow prover snark to a simpler statement than you started with. You apply it only to the first snark verifier, and so it's like you apply the fast prover to prove a really big statement, and then you apply the slow prover snark not to the original big statement, but only to the verifier of the fast prover snark. And so slow prover applied to just the verification procedure can still be a low order proving cost relative to fast prover applied to the original giant statement. Does that make sense?
Yeah, thanks.
Yeah.
A few other questions. Sorry, a few other questions from chat. So if you had more to add to mine, then yeah. So one was just like, is this stuff in the book, and if so, where? My sense is that you're now touching on things that are not in the book, whereas last week Dory was in the book.
Yeah. So this stuff about recursion and snark composition. So like prove a proof, and so that what and saying like, oh, this is like a best of both worlds thing where if this proof was generated with a fast prover, and this proof was generated with like a slow prover, but like really good verifier cost, you kind of get the best of both worlds where, because this slow prover was only applied to the verifier of this proof, all that stuff that is in the book. I think it's chapter 18, which covers recursion and folding schemes. And so, this sort of prove a proof thing to get the fast prover, but also the small proofs, that's at the start of this chapter. I think it's 18. So that's where I would recommend you have a look. But this is the prevailing paradigm, is the snarks that have the fastest provers today, or at least have a reputation for having the fastest provers. They have pretty big verifier costs, and people are not happy with those verifier costs. So they'll run the fast prover snark, but they're not happy with the proof size, and so they're not done. They will then use like a slower prover snark to prove they know that proof, and thereby get out a shorter proof. And they might even, keep going for several layers, which is what like Plonky 2 was doing, right? They would kind of run FRI with an increasingly slow prover, but better verifier costs, to shrink the proof gradually without, taking a major prover time hit. And then only once they got the proof down like fairly small to like 100 kilobytes or even maybe a little bit less, would they then switch over to something like Growth 16 or FLONK with like a really slow prover but really small proofs. Okay. Other questions?
There was a question. So are we applying recursion to turn Growth 16 into a FRI, or the other way around? And maybe I didn't phrase that question right.
No, yeah, no, I got it. Yeah. It's you use Growth 16 to prove a FRI proof.
Nice.
Okay. And so yeah, people have a term for this stuff. So let's say like if the Growth 16 proof is like pi prime and the FRI based proof is pi, I always get mixed up which is one of these is called the inner proof and one of these is called the outer proof. And I always find it like my intuition is it should be the opposite of what people actually say. But you imagine like, I don't know, that like the proof pi is like inside this proof pi prime, but pi prime proves pi. So, what one is inside the other. I always get mixed up, which is conceptualized as being inside which, but so that's what people do. And so, this proof is super small, it's like, under a kilobyte. Whereas this proof is decently big, like 100 kilobytes and up. And so that's you want the Growth 16 proof to be the final proof. But hopefully, FRI verification is simple enough that, using Growth 16 to prove, you ran the FRI verifier correctly on this pi is not like a major hit to prover time. Yeah. And so like, remember, like these FRI proofs, broadly speaking, it's like, the verifier here is doing like checking this pi is like 40,000 hashes or something, maybe, could be less or more by, factors of up to, I don't know, 5 or whatever. But that's roughly the ball, you're talking thousands of hashes, right? And so, the circuit that verifies this pi prime, like basically what that circuit is it's like, several thousand to tens of thousands of hashes, in a circuit, right? And then you're applying gross 16 to a circuit that just, does Poseidon hashing, thousands of times. That's what's happening, in the guts of, this, snark recursion technique. So there's been tons of work to, design hash functions that turn into small circuits so that, the circuit you apply gross 16 to is not that big. And so that the gross 16 proving is not some horrible bottleneck. Maybe I'm going way too deep into the weeds here, but like, I can give you some numbers. Like RISC-0 does this, with gross 16 today. And I think they say that the gross 16 prover takes 15 seconds on a GPU, which, but if you ran it on a CPU, probably, you get like a 10x speed up while GPUs over, like state of the art CPUs today. So this would be like multiple minutes. Okay. And so, I'm saying, like applying the gross 16 prover to the FRI verifier is not a prover bottleneck. And, it can be, like minutes, matters. 15 seconds might even matter, right? Because like Ethereum blocks are, what is it, every 12 seconds or 6 seconds or something. So, you definitely can't just ignore, like, you do have to go into the weeds and figure out like concretely just how slow is the gross 16 prover applied to the verification circuit of the other snark. It does matter.
Yeah, I mean, my sense is like all of these things are bottlenecks. It just there might be some other thing that's a bigger problem first, but in like yeah, we're always trying to bring down prover times.
Yeah, so I mean, it's all context dependent, right? Like if you spent, an hour, generating this proof pi, then who cares about a couple more minutes or even 15 seconds? Like it doesn't matter. But if you spent, 5 seconds generating this proof pi, then now this, recursive application of gross 16 is the major bottleneck. So everything is context dependent.
Thanks. Cool. That's it for questions.
Great. Okay. All right, so let's dive into like Ligero and Brakedown. So Ligero is, actually, it's like contemporaneous work with FRI. I think that would make it like 2019, I think. Brakedown is much more recent, and they really just differ in, they both use error correcting codes. Actually, I guess Brakedown is like 2021, although it didn't get formally published till last year. Anyway, they both use error correcting codes. I'll explain what those are in a second. Ligero is specific to the Reed-Solomon code, whereas Brakedown uses like any what's called a linear code. And actually, even the observation that you can use any linear code, in like the Ligero polynomial commitment actually dates back to the older work as well. So really, all Brakedown did was it gave like a, let's just say, a nice error correcting code to use that's not Reed-Solomon. Not a Reed-Solomon code. Okay. So they're really the same commitment scheme. You just change the error correcting code that it uses internally. Okay. So let's talk about how they work. So recall Hyrax. So I think of Ligero and Brakedown as just the hashing based analog of Hyrax. So Hyrax used elliptic curves, but the key property it used was the following. So it exploited that, if I commit to like a polynomial p, let's say it's univariate just for simplicity, but it could be multilinear. So here are its coefficients. And then so Hyrax exploited the following property. So if I write out the coefficients in a square matrix, root n by root n matrix, C0 up to C root n minus 1 in the first row, C root n up to C2 root n minus 1 in the next row, and so forth. Then the following holds. P evaluated at any point R is just a vector matrix vector multiplication, where this is the matrix. This coefficient matrix is the matrix, and the right vector is just the first root n powers of R. So 1, R squared, up to R to the root n minus 1. And the left vector is powers of like R to the root n. So 1, R to the root n, R to the 2 root n, and so forth. So you can just check this property offline, and we covered it before when we discussed hierarchs. So this key, structural property of polynomial evaluations is sort of what unlocks Ligero and Brakedown, just as it unlocked hierarchs. So yeah, this vector matrix vector multiplication is what's key here. So with that out of the way, I can tell you how Ligero would actually commit to the polynomial P. So let's do that, and then I'll pause for questions. Okay, so we have these root n rows of this matrix, each of length root n. Okay, and what the prover is supposed to do is the following. So here we're going to invoke an error correcting code. I will tell you momentarily what is an error correcting code, just in case you haven't seen it before. That's fine, but just bear with me. So the prover is supposed to take each row of this matrix and encode it with an error correcting code. Okay, so what that will do is it will add redundancy to the row. So it will kind of replace the row of length root n with a larger encoded row of length, 2 root n or something. Let me change color here. So this encoding now has length, 2 root n, where 2 could be, any constant, 3, 4, 5, whatever. And we'll see there's a trade-off between, how big this constant is and how big the Ligero evaluation proofs are. But yeah, so the prover encodes each row by row, just completely independently. So this is like the encoding of row 1. This is the encoding of row 2, and so forth. The encoding of row root n. Okay, and then the commitment is just the Merkle hash of this. So the commitment is just the Merkle hash of the encoded matrix. Okay, and as we'll see, it actually makes sense to, just as like kind of mainly a concrete performance improvement, it sort of makes sense to treat entire columns of this encoded matrix as roots of the Merkle tree. So the picture is this. So like here's your unencoded matrix. Okay, the encoded matrix has the same number of rows, but more columns. So here's your encoded matrix. Just a row by row encoding of the unencoded thing. And you would, let's say it's a systematic, code. That just means that like the beginning of each code word is the thing you're encoding. So, the encoded thing is like, the encoding of row 1 is just row 1 followed by redundancy. The encoding of row 2 is just row 2 followed by redundancy. And so it turns out like whenever we open we'll wind up opening entire columns at a time. So you sort of build a Merkle tree over the columns. So just a quick, sketch here. So, you would hash this entire column, you would hash this entire column, and then you would hash those two hashes, and you'd build a tree in this way. So you might hash these two columns separately, and then you would hash the hashes, and then, you build the tree. And so this Merkle procedure, compresses this entire encoded matrix down to a single root hash. And so the commitment, to the entire polynomial is just this root hash. So I'm going to put it in red. This one red hash, this is the commitment to the polynomial. Just this one red hash. Okay. So that is the commitment phase of Ligero. The encoding used in Ligero is the Reed-Solomon code. So what that means, just very briefly, is the following. Reed-Solomon codes are basically just univariate polynomials as error-correcting codes. So they will like interpret, when I talk about like row one, and then I say this is like, this whole thing is like the encoding of row one. What's going on here is like we interpret the root n entries of row one, C0 up to C root n minus one, interpret them like as coefficients or evaluations, however you want to do it, of a degree root n univariate polynomial, I guess root n minus one polynomial. And then the encoding is just like kind of extra evaluations of this polynomial. Maybe I don't know, it doesn't matter. Let's say evaluations. This is, some people would call this the univariate low degree extension encoding instead of the Reed-Solomon encoding. I don't know. They're all approximately the same in this context. And so, we'd be the entries of the code of the encoding would just be like extra evaluations of this polynomial. So if this polynomial was Q, encode, like you'd be interpreting like row one as like, the first root n evaluations of Q, and then the extra redundancy is just like a additional evaluations, Q root n up to Q, 2 root n or something. That's this would be the Reed-Solomon code. Okay, and like, yeah, if you want the encoding to be fast, like people actually like, the interpolating set here is not just field element 0 up to 2 root n, rather they would be like 2 root n root to unity. And I think we've discussed stuff like this before when we talked about, univariate low degree extensions for use in like, snark polynomial IOPs like Marlin and stuff. So I won't repeat the discussion in detail, but that's what Reed-Solomon encoding is. It just says, hey, the message I want to encode, I interpret it as specifying a univariate polynomial whose degree is just like the length of the message. And then the encoding is just like additional evaluations of that polynomial. So that's Ligero as a commitment scheme. That's its commitment phase. Okay, let me pause here. That's kind of, we're halfway to a complete description of the commitment scheme, because I've told you how to commit, but I haven't told you how to then evaluate the committed polynomial at a requested point. Questions?
Could you say a couple of words? Why do we need redundancy, since it feels up to this point like we can do the same without it?
Yeah, great. It's a little, so, if you used elliptic curves, you wouldn't need redundancy. That's basically what Hyrax does. A Hyrax doesn't have any, so it also does this like, row by row thing or column by column thing, is just depending on which direction you want to go, but without any encoding. Okay, the deal with these hashing based snarks is, but because hash functions like don't have the same homomorphism properties that elliptic curve commitments do, you're ultimately never going to be able to like inspect, like do, you kind of have to do a spot check, where you don't ever, the verifier never looks at the entire matrix. Okay, so somehow Hyrax like lets the verifier check information about the whole matrix, the whole size n matrix, even though the verifier runs in root n time, and it's able to do that by exploiting homomorphism that just isn't there to exploit with hashing. And so like the Ligero verifier is ultimately only going to be able to kind of spot check a very small fraction of the matrix. Okay, and that's exactly what encodings are good for, right?
Pause for questions.
What's that?
Pause for questions. Can we pause for questions?
Pause for more questions? Sure.
Yeah. Sorry. Yeah. So if that matrix is the coefficients, I guess the question is like, what is the encoding itself? Just wanted to catch up before you kept moving.
Yeah. I don't want to say, yeah. It is a little meta here. So I'm just trying. Reed-Solomon encoding, you can kind of choose it, choose to view the symbols of the message you're encoding as coefficients or evaluations of a univariate thing. And I'm just trying to decide if I should pick one and stick with it, or if it doesn't matter to answer it. So it's a little confusing where, this matrix gives you the coefficients of a univariate thing of degree n, but the Reed-Solomon encoding is happening row by row, so each row is separately, for as far as the Reed-Solomon encoding is concerned, coefficients
its own polynomial, right?
It's its own polynomial. Yes, exactly, of degree root n rather than n. Yeah,
cool.
That's right. Yeah. So this row by row Reed-Solomon encoding is very different than a single Reed-Solomon encoding of the whole size n object. Like viewing each row independently as a root n size object and encoding that is quite different than viewing the whole thing as one big size n object and encoding that.
Yep. We get root n different encodings, each of size. Like the thing that we're encoding is of root n, and then we make a Merkle hash out of that.
Yes, exactly. And so people call this row by row thing, they'll call it the interleaved Reed-Solomon code, which is not the same as the Reed-Solomon code itself. And the difference is here we're sort of encoding each row separately instead of like sticking all the rows, concatenated together as one giant thing and encoding that one giant thing. Great. And so, why intuitively is the error correcting code coming in? It's because, somehow, without homomorphism of the commitment, procedure, the verifier is only ever going to be able to inspect a very small fraction of like what is inside this Merkle hash, this red root. And so you really need a distance amplification procedure. That is, you really need something that's going to take tiny differences between two rows or something, and blow that tiny difference up into easily detectable differences, so that even if I only look at 100 entries of this row, I'm still very likely to kind of detect the deviation in some way. Is that intuition a little bit helpful?
Is it okay to say that encoding here is doing roughly the same what Schwarz-Zippel doing with pairing base or with elliptic curve base?
Yeah, I think so. I mean, Schwarz-Zippel is generally used. Well, in some sense, the distance of the Reed-Solomon code follows from Schwarz-Zippel, or the univariate version of it, which is really just like the fundamental theorem of algebra or something. So it is the same thing, right? Like so the Reed-Solomon code, has very nice distance, right? It's like two. If I have two messages of length d, and that differ, they're not the same message, that differ in even one entry, right? And that so their encodings, their Reed-Solomon encodings, have to differ in let's say the encoding has length 2d, have to differ in like 2d minus d points at least. Right. And why is that? It's because any 2 degree d polynomials can only, if they're not the same polynomial, they can only agree on at most d minus 1 points or whatever it is. And so, the fact that, two different code words in this code have to be very far from each other literally is the same thing as Schwarz-Zippel. Right. And so Schwarz-Zippel is used everywhere in SNARK design, not just with pairings, not just with curves. It's used in the polynomial IOPs and the sum check protocol to say, like, hey, if the prover sort of deviates from what it's supposed to do in any tiny way, the verifier is very, very likely to kind of catch the prover. It all boils down to this distance amplification property that itself is, if you're dealing with polynomials, is just Schwarz-Zippel.
Oh, I guess I got it. So in other protocols, when we do fetch and mirror, we bring this randomness via hashes and then apply this Schwarzschild check. Let me call it this wrong way. And here we already have this hashing when doing the Merkle tree, and it is the source of randomness, and then we and then we are back to the Schwarzschild thing again. So
Yeah,
it's kind of
yeah, that was largely correct. I mean, we haven't, nothing has been randomized yet. Like the commitment here is deterministic. The randomness comes in during the evaluation proof checking. But when the verifier goes to check an evaluation proof, it's kind of going to, pick like 100 random entries of each row, make the prover reveal those entries. And the fact that, the Reed-Solomon code word has good distance, which itself just boils down to Schwarzschild, is what's going to ensure that, unless the prover gets super, super lucky, one of these 100 entries is going to kind of reveal any lie if the prover, kind of didn't do the commitment the right way. Is that helpful?
yes, this last piece of check and deterministic versus non-deterministic is very explanatory. Thank you. Thanks a lot.
Yeah, great. Okay. Any other questions?
Yeah, can you hear me?
Yep.
So, well, I think I would ask you to break down this Merkle commitment yet another time, because I didn't understand why we need this Reed-Solomon to Merkle commit, because the whole point of commitment is like the whole structure being consistent and being binded to the commitment. So why do we need this encoding to commit?
Yeah, great. So we'll see this in the evaluation proof, which we haven't gotten to yet. But the encoding is there so that the verifier will be able to detect if the prover, is cheating in any way, via inspecting only a small fraction of like what is inside the Merkle commitment. So, you sort of another way of phrasing your question is like, why not say the commitment to the polynomial P is just the Merkle hash of the unencoded matrix?
Yes.
Yeah. So that, so no encoding, Merkle hash this thing. Okay. And the answer is that, that checking evaluation proofs is not going to work out if you don't have the encoding. Basically because to have a sublinear verifier, the verifier is only going to be able to ask the prover to open up like a tiny fraction of this matrix. Okay. And so you could imagine, what if the prover like kind of changed just one coefficient of the committed polynomial, right? Then the probability, that the verifier happens to open up the one coefficient that changed is too low. It's, the verifier has to get very lucky to happen to, choose to inspect that one tiny change. But if you have the error corrected encoding in there, it's actually, that change becomes much more easily detectable. That's the whole point of, these distance amplifying codes. So error correcting is sort of a confusing way to refer to it in this context. We don't care about we care about distance amplification. So what's going to be important is that if the prover messes with even like a single entry of a single row, that a verifier that's kind of only inspecting like a tiny fraction of that row is able to kind of nonetheless pick up on that tiny change. And that's what distance amplification gives you. Kind of any tiny change gets blown up, like winds up affecting like almost everything in the encoding. Does that help a bit?
Yeah, that helps. That helps greatly. That's kind of magic out there. Thank you very much.
Yeah, it is. And so you should ask again after we see the evaluation proof procedure and how the proofs are checked if things are still unclear at all.
Yeah. Okay. Thank you.
Yeah. More questions? Okay. All right.
Yeah,
so
one is coming up. Sorry.
there's
One is
one more.
coming up.
Go ahead.
Sorry. So this is very analogous to extending on the multivariate case.
So I wasn't able to hear that. The audio quality was pretty low.
Sorry. Can you listen to me now?
Yeah.
Okay. So just like this is very analogous to the extensions we did with the multivariate polynomial.
Yeah. I mean, like any kind of low degree extension, which is all over the place in the polynomial IOPs, like those are ultimately just error correcting codes. Reed-Solomon code literally is like univariate low degree extension. I'd say the difference here is that applying the error correcting code is a non-interactive procedure, right? Like the prover itself just like says encode and like writes down all of the needed evaluations. And then commits to, succinctly commits to them. Whereas in these polynomial IOPs, there's interaction. So it's like, when you deal with a univariate polynomial arising like in the sum check protocol, or multilinear one, like the prover might or might not like be, writing down all, a huge number of evaluations of that thing. Anyway, that was a tangent. Ignore that. Yes. It's all the same. It's you're whether you're dealing with an error correcting code here or dealing with low degree extension polynomials elsewhere in snark design, everything just boils down to distance amplification.
Okay. I did want to ask something else, but when we were checking before the encoding, I got a bit confused because the row is made up of coefficients.
Mm-hmm.
And you say we're extending that like we do the encoding.
Mm-hmm.
So at that point, if you do like Reed-Solomon encoding, you would be treating every coefficient as some evaluation. Is that correct?
Every coefficient. I didn't quite catch the last two words.
So like you would be treating every coefficient as an evaluation, and then you would be extending it by evaluating at more points.
Exactly. That's exactly right. Yeah.
Oh, okay, that's fine. I was confused with that.
Okay. Yeah. So you sort of have options, right? You could so what's important is that you take each row of this matrix, which is coefficients of the univariate thing, and interpret it as a univariate polynomial in some way. One way to do that is interpret it as evaluations. Another way would be to interpret it as coefficients. You kind of have your choice. But then the Reed-Solomon encoding definitely will be, however you interpreted this thing as a polynomial, the encoding will then be evaluations of that polynomial. If so one nice thing is if you just stick with evaluations all the way through, so you interpret the message as evaluations and then the extra redundancy as evaluations as well, then the code is systematic, where the message itself is the first part of the code word. And so I think that's nicest. So I guess, even though you have flexibility, let's just stick with that. So let's go. So exactly what you said is what we'll stick with. So you interpret, the entries of this row as evaluations of a univariate thing, and then the encoding is just more evaluations of that. More questions?
Nope.
Great. Okay. So just a reminder, where we are in this protocol description. So, if I want to commit to a univariate polynomial, I just write out its coefficients as a matrix. I take each row of the matrix, I apply an error correcting code to that row, and then the commitment is the Merkle hash of the encoded matrix. So just this root hash right here. That's it. Okay. Now, so the way I like to present this is not to jump straight to evaluation proofs, but to imagine, let's say you're the verifier who just received this commitment. So the commitment is just this one Merkle hash, just this one hash. So, you get like one hash value, that's it. And you want to know, like, is the matrix inside this hash, is it sort of well formed? Okay, and by well formed, what I mean is every row of this matrix a code word in the code? Right? If the prover is honest, then every row of the matrix was encoded with the code, and then it was Merkle hashed, right? So if the prover is honest, every row of the matrix inside the commitment is a code word in the code. But if the prover was just trying to mess with you, maybe some of the rows are not actually code words in the code. Okay, so let's talk. I call this like a testing procedure. Pen just died. Let me charge it for a minute. I call this a testing procedure. Now, in practice, you actually don't need the testing procedure at all. You can kind of jump straight to the evaluation proofs, which turn out to look exactly the same as the testing procedure. But I think it's easier to conceptualize what's going on in the evaluation proofs as a testing procedure instead of an evaluation procedure. So I will tell you momentarily how this testing procedure works as soon as my pen gets a little charge on it. So verbally, this is what's going to happen. Okay, the verifier is going to say to the prover, "Hey, I want to know this particular random linear combination of the rows of the encoded matrix." Okay. So the verifier is going to say to the prover, "Hey, here's a bunch of random values, R1 to R root n. Okay, I want you to send me the random linear combination of the rows of the matrix inside the Merkle hash, where R1 to R root n are like the coefficients in the random linear combination." So the verifier says, "Hey, send me what it's like I equals 1 to root n of Ri times rho I." Okay. All right, and let's say rho I of the encoded matrix. Okay. That's what the verifier requests. And so the prover sends, like a vector W, which is claimed to equal, what the verifier just requested. So claimed to equal this particular, linear combination of the rows. And what the verifier does is it checks two things. One, that W is a code word in the code. Okay, and two, it's going to sort of spot check that W like indeed looks like or is the requested random linear combination of the rows. Okay, and I'll explain in more detail now what all that means. Okay, let's start with elaborating on this property one that the verifier checks, that W is a code word. Okay, so let me explain first that if the prover is honest, then W will definitely be a code word. Okay, why is that? So that's what it means for an error correcting code to be linear, and Reed Solomon is an example of a linear error correcting code. Okay, so like what's going on here is if each row, if the encoding is interpreting each row as like a degree root n polynomial, if I take a linear combination of a bunch of degree root n polynomials, what comes out is also a degree root n polynomial. Okay, another way of saying that in coding theoretic terminology is if I take a whole bunch of code words in the code and I, take a linear combination of them, I just like add them together, what comes out is still a code word. Okay, so that's why, if the prover is honest, then as long as every row is a code word in the code, which it will be the case if the prover is honest, I can just like add the rows up willy-nilly, and what will come out is also a code word. Okay. So yeah, and the converse turns out to also be true in a sense, which is if there is any row that is not a code word, then with overwhelming probability, random linear combination of the words will also not be a code word. So I'll elaborate on this shortly. So like kind of the fact, what completeness is sort of clear here. Again, if every row is a code word, then the random linear combination of the rows will also be a code word. Soundness, that is, if any row is not a code word, then the random linear combination will also not be a code word with overwhelming probability. That is a deep fact, which I will elaborate on shortly. Okay, and then let's talk about the spot check. So it actually turns out.
Excuse me,
Yeah,
before
please.
we go, where random values come from, FRIs?
Great. So in a snark, they would come from Fiat Shamir. So you would be like Fiat Shamir hashing the Merkle commitment to get view these as random verifier challenges. In an interactive protocol, they would just come from the verifier. Okay.
Yeah,
And
I see. Uh-huh.
and it might be a little annoying that there's root n random values here. It turns out that with some small loss in security, there can actually just be one random r, and r1 can be like 1, and r2 can be like r, and r3 can be r squared, and this can be like r root n minus 1. So if you don't like having such a long verifier challenge, root n random field elements, you can actually just pick a single random field element and take powers of it.
I see. I just thought that maybe it comes from the Markov tree itself or something like that. Thank
Yeah,
you.
no, it's a random verifier challenge. So Fiat Shamir or the verifier. Yeah. Thanks for the question. Any other questions?
There's a question in chat that I don't entirely understand. We'll see if you do. It says, so FRI is used to prove that a polynomial has a certain degree bound. Is the same true for Ligero?
Great. Okay, so it's a slightly different. So FRI is often formulated, as you said, as what's called a low degree test. So that means, as you said, in FRI, the prover is supposed to take like all n coefficients, as one big vector rather than a root n by root n matrix. Read Solomon encode that whole thing, size, 2n or 3, 4n or whatever, and Merkle hash it. Okay, so that's FRI. It doesn't do a row by row thing. It does everything as one giant object. And then it's called a low degree test, where the question is, if the prover was honest, then, all 2n or 4n or however many evaluations there are consistent with the degree n polynomial. And FRI is meant to figure out, like, is that the case? So is this actually a degree n polynomial? Okay, so you call that a low degree test. Okay, what Ligero is what's called a polynomial commitment scheme, where the prover wants to commit to this degree n polynomial, but the question then isn't, did I actually I'm describing it as a something very similar right now with a testing phase, but the testing phase is not testing literally like are these n coefficients or sorry, is this big vector I don't know, is okay, sorry. This testing phase that I'm describing now, it's not quite the same as testing like, is the committed thing inside the Merkle hash a degree n polynomial, right? It's testing, is each row of the committed thing a degree root n polynomial, which is a different question. Okay. It turns out that you can take this thing, is this a degree n polynomial, which is called a low degree test, and sort of indirectly use it to give a polynomial commitment scheme. So indirectly gives a polynomial commitment. Okay, and similarly, as we're about to see, the question that we're answering here with the Ligero testing phase, which is asking like, is each row a degree root n thing, rather that is also sufficient to give a polynomial commitment scheme. Okay, but to summarize, formulating FRI as a low degree test, this length, 2n or 4n vector inside a Merkle hash, formulating it as testing, is that vector like actually like all evaluations of a degree n polynomial over some specified subset. That is a little different than what we're testing here. But both tests are sufficient to yield a polynomial commitment scheme, which is what we're actually after. Okay, was that a clear enough response?
Yep.
Okay, and so just as a reminder, a polynomial commitment scheme says I want to be able to commit to this polynomial P, and later have the verifier say, hey, I want to know P of R. Please tell me P of R, and prove to me that you're being honest here. That's what we're really after here. A low degree test is sufficient to give that, but in and of itself is not quite that.
Yeah, I just didn't know that was a thing, that there was this sort of separate low degree test. And just want to confirm, that's what FRI is. So FRI is not a PCS, it is just a low degree testing tool.
Yes, but it's known how to take a low degree testing tool and in a block box way give a polynomial commitment.
Would it be fair to say that people are often referring to that black box wrapper around FRI as FRI?
Actually, no. But this is a bit of a meal to get into. So
Cool. We don't have to. I just wanted to kind of establish that distinction that FRI technically is not a PCS, but as you're telling and describing, with a little extra work, we can get a PCS from it.
That's right. But I will add the one sentence because I think it is helpful. You'll often hear of FRI being applied, quote, above the unique decoding radius of the Reed-Solomon code, which is a technical term that will make a little more sense by the end of today's session. But it turns out if you literally want a polynomial commitment scheme, you cannot analyze, you cannot go beyond the unique decoding radius of the error of the error correcting code used in FRI, which is Reed-Solomon. So it turns out that in order to get a snark, you don't really need a polynomial commitment scheme. A slightly weaker object is acceptable. And so when people actually use FRI, they are not quite using it as a polynomial commitment, in fact. And they do that because going beyond the unique decoding radius lets you make the proofs a little bit shorter. So maybe it's saving them like 2x or something on the proof size. So that's the extra color. So these notions are very closely related. They're not the same. Their differences actually matter if you care about factors of 2 in the proof size.
Nice. Yeah, thanks for breaking that down. I think that's super interesting. So just putting it in my own words. So FRI is not a PCS, but it is often used in the same kind of role as PCSs play in snarks. Because it turns out we don't actually need entire PCS, we can use something slightly weaker, and FRI can fit in there.
Yes, exactly.
Nice. Thanks.
And all of that is sufficiently deep in the weeds that I think it's actually not that widely understood what I just said. Like experts get it, but like it takes quite a bit of expertise to grok that. It's pretty deep in the weeds. Yeah. Okay. Yeah. So cool. Hopefully that's all the questions for now. Okay. So yeah. So what's going to happen is the verifier, requests this random linear combination of the rows. Maybe. Yeah, so I'm using R to denote the randomness there. That might get a little confusing because I typically use R to denote the evaluation point during the evaluation phase. So I'll just use something else to denote the evaluation point later. Okay, so the verifier checks that when the prover sends a vector and says, "Hey, this is the linear combination you requested." The verifier checks that vector is a code word. If the prover is being honest, it will always be a code word. Okay. It turns out if the prover is being dishonest, as I'll explain soon, this deep fact. If the prover is being dishonest, then the code word that the prover does send, this W, will actually have a lot of disagreements with the true random linear combination. Okay, and that's where the error correcting properties of the code come in. So as a result, so the prover sends this W. So what the verifier will do is it will randomly pick a bunch of entries of W. Okay, think like, I don't know, 128 entries or something. Where's 128 coming from? Roughly speaking, each selected random entry is going to give you one bit of security is how you should, think about it, per entry that's selected. And so if you want 128 bits of security, then you're going to need 128 entries. And so what the verifier is going to do is it's going to ask the prover for each selected entry, it's going to ask the prover to open up the whole column, the whole committed column. Okay, and it's going to be able to compute the actual linear combination of that column and compare it to W at that column, right? And so what's going on is like if W is not actually the requested linear combination of rows, as we'll see from this deep fact, it will differ from the true linear combination at like 1/2 of its points or something. Okay, and exactly how big a fraction this is actually depends on the distance of the code. Okay, so the bigger the distance of the code, the bigger this fraction, this difference fraction. And so, if you're using Reed Solomon, like the longer the code word, so like the bigger the committed, encoded matrix, the better the distance, so the bigger this fraction is. Okay.
Is just a vector. Is W a vector or?
Yeah, W is a vector, so it has length like 2 root n or 3 root n or whatever. Okay, and the verifier is going to pick like 128 entries of this vector of length 2 root n or 3 root n, and it's going to make sure that just those entries are what they should be. Okay, so it's going to, for each of those 128 entries, it's going to open up the entire column. And if W is the right vector, then this entry, like let's call this WJ. If the prover is honest, then WJ should be like, R1 times, row 1 comma J, like the jth entry of row 1, plus R2 times the jth entry of row 2, plus ... plus, R root n times the jth entry of row root n. Okay.
Now I see. Thanks.
Yeah.
Sorry for the interruption.
No, yeah. Thanks for the question, so that everything's clear. And so that's it. So the verifier will wind up, let me switch back to black. So V accepts, if, 1, W is a code word in the code, and 2, everyone, for every one of the, 128 or so entries selected of W selected, indeed, let's call them entries WJ of W selected. Indeed, WJ is the same as like sum over rows K of RK times, the jth entry of that row. So this is, this is just checking that like, WJ is what it should be given the committed matrix. Okay. So that's the testing procedure. So that's how the verifier, confirms with high confidence that, the matrix inside the Merkle hash really has each row be a code word in the code. Okay, so I'll come back to explain. So soon I'll come back and explain, why, this is secure. I've sort of hinted at it already, that basically if the prover sends the wrong W, then this W that it sends will kind of differ from the right W, at like half of its entries. And so the probability that all 128 entries do not differ is at most 2 to the minus 128, just sort of boils down to that. But I'll repeat that in a little more detail shortly. Let's talk about the evaluation proofs. Okay, so it turns out it's actually an observation of Diamond and Posen that you don't have to run the testing procedure at all. So that the evaluation proofs themselves are basically identical to the testing procedure. So there's no reason to test and evaluate you can just evaluate. So don't have to test, can just go right to evaluate, at least so long as the requested evaluation point is random, which in Snark applications it always is. It's like there's some polynomial IOP, and like the point of the committed polynomial at which the verifier needs to evaluate the committed polynomial is selected at random. It's like a random verifier challenge, so it's a random point. So evaluation proofs. So let's say the verifier wants P of Z. Yeah, normally I say P of R, but I already used R today for the testing procedure. Then remember I said like P of Z is the same as take the matrix, unencoded matrix, multiply it on the right by like the first root n powers of Z to the root n minus 1, and on the left by powers of Z root n. So Z to the 0, Z to the root n, Z to the n minus root n, or whatever it is. And so this here is a random linear combination of rows. Of the unencoded matrix. Okay, but remember, like the rows of the unencoded matrix are like this. The if we use a systematic code, are the beginnings of the rows of the encoded matrix. So it doesn't really matter that I have unencoded here. It's all sort of the same because the unencoded thing lives inside the encoded thing. Anyway, so what the prover will do is it's literally the same as the testing phase. So the prover will just send this. Like the left multiplication vector, call it W, and the verifier will do what I said above. The verifier picks like 128 entries of W at random. I guess this maybe so the prover sends like the encoding of W, let's say. The verifier picks 128 entries of that encoding at random. And checks them for consistency with the commitment. Checks for consistency exactly as I described in the testing phase. These 128 columns that were getting opened up. This pink column was one of the 128. If those checks pass, the verifier outputs. So the prover would have just sent it, this W here, I'm calling this W. So the verifier would just output W inner product, the right vector here, Z0 up to Z root n minus 1. Okay, so that's what Diamond and Posen observed is like, if you look at evaluation procedures, it's literally identical to the testing phase. Where the prover is sending a random linear combination of the rows of the unencoded matrix. So there's no reason to test and then do the evaluation procedure. The evaluation procedure itself is the same as the testing procedure, just with the linear combination kind of like what are the coefficients in it coming from the evaluation point rather than add fresh verifier randomness. So that's Ligero as a polynomial commitment scheme. Okay, does anyone want to ask any questions before I explain why it's secure in a little more detail?
One question coming up on stage.
Hi, yeah, had a question. So there's a slight difference, isn't there, between the two phases that you mentioned. So like in the was it the testing phase? The testing phase, you use the encoded matrix, and in the evaluation phase, it's the unencoded matrix. But you still, in both, you still the verifier still chooses 138 entries from this W thing. So it doesn't matter that the matrices are different in the two phases then.
Yeah, so I did sort of gloss over this a little. So the 128 random entries definitely have to be from the encoded stuff, right? So like the evaluation proof verifier sort of only cares about the unencoded stuff as far as the computing the evaluation goes. but it needs the encodings for consistency checking, right? Because it's only spot checking. It's only doing 128, kind of random inspections. It really needs the distance amplification properties offered by the code for that to be secure. And so probably the easiest way to explain, how to ungloss over what I glossed over, is the following. So here, when I said W is a code word, that the verifier checks that. The easiest way to make sure this W is a code word is to actually not have P send the encoding. Have P send the unencoded thing. Have P send W, which is not encoded. And then have the verifier compute the encoding of W on its own. Right. And then now the verifier knows for sure that this thing is a code word because it did the encoding on its own. So it sure as heck knows it's a code word. And so now there's no check here. There's nothing to check. The verifier knows it has a code word here. But now this would no longer be, this would be encoding of W. And so now there really is no gap. Now when I say, hey, the prover sends this unencoded thing, left vector here times matrix. If I call that W, now the testing phase and this thing are identical. And so the prover sends W and the verifier computes, the encoding of W on its own. And now the 128 entries that are kind of spot checked for consistency with what the prover actually committed that's inside the Merkle hash is all done on the encoding. Did that clear things up a bit?
Yeah, a little. So actually, what gets sent by the prover is not the code word W, but its pre-image.
Yes. Yes, exactly. Yeah. So this is probably just going to confuse things more. But I will mention there's been works that start to look at compose, they're not happy with the square root n proof size here. And I'll discuss verifier costs in detail shortly. But clearly, if it's a root n by root n matrix and the prover has to send a linear combination of the rows, well, that's a root n size vector. So clearly the proof size is at least root n, and it's actually worse than that because there's 128 spot checks that each require opening a column, and each column is also size root n. So people, generally don't like that the proofs are that big, and so what people have considered is some kind of something like composition, where rather than the prover explicitly sending this W, this linear combination of the rows, instead it commits to W. And then when the verifier needs to know 128 entries of W, well, it's just going to open up the commitment at those 128 entries. But there are all sorts of complications that come up, because you also have the 128 column openings, and you don't want the prover to have to send those. It gets to be pretty complicated, which is why there's paper after paper on this topic. It's like if the prover winds up committing to W rather than sending W in the clear, well, what does committing W mean? It means encoding it with some error correcting code and Merkle hashing the result. So the reason the reason I bring that up, even though it's probably a tangent and just confusing things further, is to say the reason the prover can get away with sending the unencoded thing here is because we're okay with square root n sized costs. That's what lets the prover send the unencoded thing and just have the verifier do the encoding itself. It's because the verifier doesn't mind reading the entire unencoded thing and spending root n time encoding it. Actually, it'd be root n log n time if it's Reed Solomon coding, because that's quasi-linear instead of linear time encoding. So that we can only get away with that whole thing because we're satisfied with root n or worse verifier costs. But yeah, hopefully that color was not just confusing.
Yeah, it helps. Thank you.
Can I ask something? I'm wondering, in the case of the opening, could you expand a bit on how the opening, like, does the prover send the whole column to the verifier and the Merkle proof, or how
Yes,
does it?
yes, exactly, and that's why it made sense to treat entire columns as leaves of the Merkle tree, because so if you just sort of Merkle hashed, like, the whole encoded matrix, not sticking an entire column at the leaves, then every column opening requires sending square root n different Merkle authentication paths. But here, if you sort of stuck an entire column at each leaf of the Merkle tree, when the verifier goes to open up a whole column or request the opening of the whole column, the prover can just send the whole column and then a single Merkle authentication path to authenticate that the prover opened the column correctly. Yeah. So those yeah.
No, sorry, you mean like what you were meaning, like one element each leaf, but in this case we have like the whole column is a leaf.
Yes, exactly. The whole column is a leaf. So it's yeah. So this leaf is sort of like storing like the hash of this giant root n size vector. And that way there's only one Merkle authentication path needed to open the whole column instead of root n different Merkle authentication paths. And that actually saves a log factor in proof size and verifier time.
Okay, great. Thanks.
Yeah, and maybe while we're talking about this, it's worth. So I think a bunch of the prover time benefits of something like Ligero over FRI, which again, like experimentally, people see it's an order of magnitude. It's not a small difference. There's sort of two benefits at least that are evident right here. So one is it's nicer to do root n different FFTs, each of size root n, which is what comes from encoding each row independently, versus one giant FFT of size n. Okay, so that's one thing that's nice. It's both like easier to parallelize, and you actually save a factor of 2 in the asymptotics because FFTs are n log n times. So like, log root n is 1/2 of log n. And the other thing is, you often find that Merkle hashing is slower than the FFTs. And there you get benefits because like modern hash functions tend to be optimized to hash large files quickly. So if you hash like many tiny things, it's much slower than hashing them as one giant thing. And so here, by hashing an entire column at a time, you take advantage of that. Whereas with FRI, it really is like you have a length n vector, and you're more or less like just building a Merkle tree over that vector, and so you're kind of just hashing each field element at the leaf, and then hashing those hashes, and everything is small pieces getting hashed. So those are two significant benefits for the prover for doing like the Ligero breakdown thing. The downside, of course, is root n size proofs is pretty big. Okay. Other questions? Okay. All right. So let's talk about verifier costs real quickly, and then we'll do more, a little more color on why this is all secure, why the prover can't cheat without getting caught with overwhelming probability. So remember, the prover sent this random linear combination of the rows. So this was like root n field elements. Okay, the verifier encoded W, and then the verifier asked for the opening. I guess the prover opened like 128 columns. Okay, and so because so W has the length of like one row, but these openings have the size of like 128 columns. Okay, so there's an asymmetry here, where you're sort of the prover is sending just one row, but is sending 128 columns. So to balance these two costs, which is what makes sense to minimize proof size and verifier time and all that, you actually don't want a square matrix. So you actually want the matrix to be, I I always get confused which is which. You want the columns to be smaller, so fewer rows. So you want root n, square root of n over 128, or however many columns you're opening, rows, and square root of 128 times n columns. And that will balance these two costs so that like the proof size is basically like square root of n times 128 field elements. Okay. And so this little optimization to balance the cost, I mean, it makes a big difference. Compared to a square matrix, this is square root of 128, which is about 10 times smaller, than if you didn't do this balancing, than using a square matrix. Okay. And the main thing that the verifier does is confirm that like all the columns were hashed correctly. Now you do have to worry about encoding not being too slow, encoding this like root n size thing, because that is like like root n log n field ops if you're using the Reed-Solomon code. But I think slower than the field ops is the hashing for sure. So the verifier time is dominated by like the square root n times 128 hashes. Is dominated by hashing that many field elements. Okay, so this is how to think about like the verifier costs of Ligero polycommit. Basically, the verifier is dominated by just doing all these hashes, and this is how many hashes there are. So this is something like about 10 root n hashes. Okay. Okay, so that's the verifier cost again. And let's talk about soundness. So the key to soundness is the file. I'm just going to state it as a fact. When stated this way, it sounds very intuitive, but there's actually a whole literature on proving facts of this form. So what is it that enabled the verifier to just spot check 128 columns, right? Like, remember the verifier ignored everything in the committed matrix other than the 128 random columns it opened. So what kind of distance properties of the error correcting code enabled it to only inspect these 128 columns? Here's the key fact. So say I have root n vectors. I'll call them v1 to v root n. It really doesn't matter how many there are. And even one vi is far from being a code word. Okay. So what do I mean by that? So say that is the vi, differs from every code word. Every code word, I don't know what I want to call it, u, in at least a delta fraction of entries. Okay. Okay, so it's like not only is vi small, like far from any, like, sorry, how do I want to say this? Not only is vi not a code word, but it actually has pretty good, difference from every code word. Okay, so the key fact, and this is called a proximity gap for the code. The key fact is that it turns out any linear error correcting code satisfies this property. A random linear I can just thought again, but a random linear combination of the VIs will also be delta far from the code. Okay, with very good probability. I'll tell you the probability in a second. Okay, so with probability at least something like n over size of field, where n here is, I forget if it's like the length of the code, the length of these vectors, or the number of vectors. I think it's the length of the vectors. With at least this probability, roughly, a random linear combination, RLC for random linear combination of the VIs will also be, delta far, at least delta far from the code. And by delta far, I mean delta fraction of entries, of this random linear combination disagree with, for each code word. Okay, so the way I would put this is like one bad apple, spoils the whole batch. It's like if there's a single vector in your collection that is far from all the code words, if you take a random linear combination of the collection, of the vectors in the collection, what comes out will almost certainly be just as far as that one bad guy. Okay, and so if you do the whole soundness analysis to show that Ligero is secure, there's sort of like two cases, right? Like, so one is when the prover commits to this matrix, which is each row is supposed to be a code word. It's sort of there are two ways it can try to cheat. So one is to have one or more rows be very far from the code. Okay, and if that's the case, you apply this proximity gap result, which tells you that the random linear combination of the rows will also be very far from the code with overwhelming probability. Okay, but the thing that the verifier spot checks consistency with is a code word, right? And so that's exactly why spot checks are enough, right? So like if the true random linear combination is far from the code, but the prover is forced to send a code word, say by sending an unencoded thing and having the verifier encode it itself, that means that there's the true random linear combination and what the prover claimed to be the linear combination differ at many entries, like a delta fraction of their entries. And that means the chance that all 128 selected entries are not in the difference set is really small. Like, so if they differ at half their entries, if delta's a half, then this would be like 2 to the minus 128 probability that every one of the 128 selected entries is not one of the difference ones. Okay, and then the other possibility is that like the prover, while no column is far from any code, so the other possibility is that every column is close to a code word. Okay, and then it turns out that like with decent probability, like the evaluation proof is just like unaffected, or so there's a way to deal with that case. I'll wave my hand and just ignore the details. So yeah, to summarize, there's a way to say like the only kind of cheating you have to worry about is that there is one or more rows of the committed matrix that is far from any code word. And then the proximity gap saves the day. It tells you, whatever the prover sends, because that's forced to be a code word, will also be far from the true linear combination of the rows. And so the verifier will detect an inconsistency within one of the 128 open columns with overwhelming probability. Okay. And so the same kind of proximity gap results also underlie the soundness of FRI. So the first paper to prove this was the Ligero paper, but there have been tightenings of the results that have come subsequently, mostly motivated by FRI, because that's been the popular one. But I think over time, people will understand that, like FRI is sort of optimized for verifier cost, but doesn't have the fastest prover, and that maybe the popularity of things like Ligero and Brakedown will increase. Okay, so the closing notes, because we're basically done here. I think the main thing I want to discuss is Binius. Let me just collect my thoughts for a second. Is there anything else I wanted to say something about real fast? So I want to talk Binius, and I want to discuss Breakdown, and also like how does code distance affect snark performance. So this will only take a few minutes, I think, to cover both of these topics before we wrap up. But let me pause here since I just sketched the soundness analysis in a little more detail. This proximity gap stuff. Does anyone want to ask any questions about this?
Looks like no.
Okay. So a few things I want to highlight then. So this right here, this probability being, like vector length over field size. This is why like all hashing based polynomial commitments like need a 128-bit field. Okay. If you want 128 bits of security, I mean, even with 128-bit field, you actually can't get 128 bits of security here. Like this n would have to be 1 to get 128 bits of security out of this. There's a lot of efforts to quote like work over small fields with hashing based commitment schemes. And that's a little bit of a misnomer. For the hashing based commitment scheme to be secure, you have to work over 128-bit field no matter what. In fact, you maybe even should go a little bigger because this is n over field size and not 1 over field size. So what people try to do is have the 128-bit field be of small characteristic, which means it's an extension field of a smaller field, and they try to keep as much of the prover's work over the small field as possible. Okay, but ultimately, when you do this, like random linear combination of rows thing, that has to be over the 128-bit field. Okay, so there are some projects that are using a 124-bit field. I think they're being quite aggressive because n over 2 to the 124 is could easily be under 2 to the could easily be less than 100 bits of security and stuff like that. So when we discuss Binius in a moment, that's going to be relevant. Okay. Before going to Binius, let me come to Breakdown and code distance. Here's the situation. So properties of the code translate to snark performance. Okay, so like the snark prover has to encode, each row of the matrix that it's committing to. So faster encoding, okay, means a faster snark prover. Okay. Now you can't take this too far because Merkle hashing rather than encoding may well be the prover bottleneck, and the cost of Merkle hashing is actually not determined by how fast it was to encode, but rather like how big are the code words. But generally speaking, because the snark prover has to do a lot of encoding, if you have fast encoding, you're going to have a faster snark prover. Okay. Code distance. So encoding time matters. Is one way that properties of the code translate to snark performance. Code distance translates as follows. Better code distance means shorter proofs. Okay, so basically, the better the code distance, the fewer the columns, the number of columns you have to open. And hence the shorter the proofs. Right, because you could think of it like the bottleneck in proof size is opening like 128 columns. If I had a code with worse distance, maybe I have to open 512 columns, and now I've 4x'd the number of columns I'm opening, and that actually turns into like a doubling of proof size after you kind of balance all of the costs in the snark. So we like codes with good distance. because it leads to short proofs, but distance really doesn't have anything to do with proving time. It's like encoding time is what determines proving time. Code distance is what determines proof size, which is relevant to verifier costs. Okay, so what Brakedown did was it gave a code with asymptotically faster encoding than Reed-Solomon. So order, let's just say linear encoding time. Reed-Solomon encoding time is n log n. This is order n. That's been known for a long time, theoretically. What Brakedown, really the main contribution was giving a code that was reasonably practical in the context of snark design. So the theorists all thought that these linear time encodable codes were impractical. No one really uses them in coding theory contexts, but the snark context just kind of cares about different aspects of the code than coding theorists care about. And so, we could make them practical for our context, even though they were regarded in other contexts and still are as impractical. Now, the distance here is not great. So distance of I think of the Brakedown code is like maybe like 1/20th. Like any two code words differ in at least like 1/20, like 5% of their entries, or something. Whereas if you used a Reed-Solomon code, it'd be much better. Maybe it'd be like a half rather than a 20th. So the deal is here, Brakedown got like faster, encoding, which is faster for the prover, but much bigger proofs than using Reed-Solomon. Another nice property of the Brakedown code is it sort of works over any field, whereas if you use the Reed-Solomon code, you sort of need an FFT-friendly field for encoding to be, nice and fast and stuff. So yeah, Brakedown was just exploring, well, what if you move away from Reed-Solomon to other codes? Can you get some nice properties that you can't get with the Reed-Solomon code? And the answer is yes, but it comes at a cost because the distance of the code, we came up with is worse. The proofs are bigger. And, there's been some more recent work like Blaze, which is looking at yet other codes. So other, codes that are not Reed-Solomon, but also different than the code in the Brakedown paper. Okay, and so that is the Brakedown line of work. Let's come to Binius. So with Binius, Binius I think is really important. I sort of think like the fastest snarks are eventually going to be based on the technique I'm about to describe. And I guess I'm motivated by, as soon as my pen charges a little bit, by bringing up this fact I stated before, which is for security of the commitment scheme, you have to work over a 128-bit field. You just really have no choice. Despite this sort of, small field terminology, this random linear combination of rows has to happen over a 128-bit field. Okay, so there's the question, like, what if I want to commit, let's say, just to bits, so to like, say, a ton of values, very, very many values, but all of them are in 0, 1. Okay. The old way of doing this would have been to sort of assign each value, even though they're kind of the smallest possible values, they're just 1 bit each, 0 or 1. We sort of assign each one an entire field element, a 128-bit field element, and apply your favorite, hashing-based commitment scheme, whether it's Ligero or FRI or whatever, to that polynomial, right? That is like, if the polynomial I want to commit to is, I'll stick with univariate here, sum from I equals 0 to n minus 1 of ci times x to the I, and even if all of these CIs were just zeros or ones, the old way of doing things would have been, just treat P, this polynomial, as a polynomial over your 128-bit field. Whatever field you're using, your 128-bit field, and go from there. And so that means, the vector I'm encoding, whether I view it as a root n by root n matrix or a length n vector, FRI views it as a length n vector, Ligero would view it as a root n by root n matrix. It's n, 128-bit field elements, and the random linear combination of rows or whatever is going to happen over the big field. Okay, and like if you work over, like a field of characteristic, 64 bits or 31 bits, like maybe you can do a little bit better than this, but only a little bit. Okay, so here's what Binius does. So Binius will say take your n bits, 0, 1 values. Okay, and pack them, if you're the committer, pack them into n over 128, 128-bit field elements. And you actually have to work over a binary field for this to all work out. So this is a 128-bit field, of characteristic 2. So there's a unique field of characteristic 2 that's 128 bits. And so we have a 128-fold reduction in the number of field elements we're committing to. Okay, so let's call that like I don't know, P packed. Okay, so now P packed has degree, not n, but n over 128. So if P was, I don't know, I'm just going to write a bunch of random bits here. If this were the first 128 bits of, that the prover wanted to commit to, what we would do is interpret, all 128 bits as a single one field element. And there are very natural ways to interpret, any 128-bit vector as an element of GF2 to the 128. So we're just gonna do that. And so now what we apply Ligero or Brakedown to, it would be or FRI, because FRI Binius is just like an adaptation of FRI to the Binius's setting of working over this binary field. Now every if it's FRI Binius, it's 1 vector of length n over 128. If it's Ligero, we'd be dealing with, square isn't optimal, but something like root n over 128 and root n over 128. So you get this 128-fold reduction in size of the committed thing. And now everything you're committing to is over the big field. And so you can apply, Ligero, Brakedown, or FRI, and have your security. Okay, and then we're not done. Like, if that was all you had to do, and there weren't any issues with that at all, it would, you wouldn't need like a breakthrough paper, like I consider like Binius and FRI Binius to be. That would just be like the like trivial thing to do. So what's the problem? So the problem is like the snark verifier, needs ultimately to evaluate the unpack thing, to evaluate P, which has, degree n, but the prover committed to P packed so it needs to evaluate, P of R for some, P, I'll call P of Z for some Z, but the prover didn't commit to P, it committed to P packed. Okay, so what we need is, we need a way to relate P of Z, which is what the verifier wants, this is what V needs, to P packed at some other point. Okay, and how do they do this? So this ultimately got when the first like Binius paper came out, it wasn't really clear like where in the protocol this was happening. Was it part of the commitment scheme? Was it elsewhere? Now it's very clear. So the Binius guys have something called the ring switching PIOP. If you look at Blaze, it does something very similar. that's actually a little more straightforward conceptually. Blaze does something more straightforward, but ultimately is follows the general high level outline I'm about to describe. So you express P of Z as a big sum, say J in 0, 1 to the L for some L of, I'm going to wave my hands here, like, evaluations of P packed. Okay, so somehow there is a way to relate the desired evaluation of the unpacked thing, which is what the verifier really cares about, to evaluations of the packed thing. Okay, and so you just compute the sum, like you just apply the sum check protocol. Okay, and at the end of sum check, the verifier needs to evaluate, what sum check was applied to at a random point. So V needs P packed, of Z prime, for some random Z prime. And now we're good. The prover committed to P packed. And so, with Ligero or Brakedown or FRI or FRI Binius, and so it can just provide the evaluation with an evaluation proof. With the evaluation proof. So that's it. So the key insight into this Binius line of work is, if we know the values we're committing are small, you can pack many of them into a single 128-bit field element. You have to ultimately work over 128-bit field element for security, over 128-bit field for security. But now, rather than each 128-bit field element representing like a single value, it's actually representing like 128 values all packed into one big field element. And the snark verifier cares about the unpacked thing. That's like kind of what the prover really wanted to commit to. It just wanted to do it in a faster way to bridge the gap between the fact that it actually committed to this packed thing, but the verifier cares about the unpacked thing. You just express, the desired evaluation of the unpacked thing in terms as a big sum of evaluations of the packed thing, and you hit it with sum check. And at the end of sum check, the verifier just needs to know the single evaluation of the packed thing, and now you're good, because that's actually what the prover committed to. Okay, and so this makes it, like roughly like 128 times faster, than the very naive thing, at least, to commit to 1-bit values, to 0, 1 values. And so working over, like Baby Bear or Goldilocks or M31, these 31-bit fields, it's still, like 30 times faster to commit to these 1-bit values with with something like Binius, than like FRI, probably more than 30x, just because FRI is also fairly slow, as I've been saying, but then FRI over M31 or Baby Bear or whatever. Due to this, here you would, you're still you're spending 31 bits, a 31-bit field element, to represent a 0, 1 value. Whereas in Binius, you'd be, a single 128-bit field element can represent 128 0, 1 values. It's sort of maximum, they call it maximum information density. It's kind of using every single bit of the field to actually represent data you want to commit to. So as I think we might talk about next week, this ability to commit to small values really fast is really important. So that will become clearer next week. But I think intuitively, like 0, 1 values arise a lot. You want to evaluate Ketchak or Shah or something, and that's just very naturally represented with Boolean values. And so committing to zeros and ones super fast is obviously a nice thing to be able to do. And I'm releasing this paper soon on memory checking arguments that kind of exploits fast commitments to 0, 1 values in a more extreme way. Okay, so hopefully that was a useful overview. Binius and this packing stuff and Brakedown. So that's all the hashing based schemes in quite a bit of detail, other than FRI. So I think next week maybe we'll talk about memory checking arguments, and then the following week we'll do FRI. Okay, questions?
Nope, not in the chat.
All right.
Cool. Thanks. See you next
Okay.
week.
Yeah. Thanks, everyone. Have a great week. I'll see you next week.